Alright, so here's a really neat little simulation to demonstrate the two things, amplitude and frequency. Okay, so string displacement. So what it is that this is meant to be a guitar string. Where obviously you pluck the string and the string displaces. Now what it does is it affects these air particles, which are the little dots you see here, and the sound wave then progresses from this vibration through the sound, or through the air particles. So it's transmitted longitudinally through the air particles. And then with the string tension, we're in a position to change the frequency. So let's just go do that and you can get an idea. Okay, so with zero displacement, or very small displacement, you can see a small little oscillation there. You have a very faint sound. However, when I increase the displacement, we expect it to get louder. That's exactly what happens. So I'll increase the displacement again. And there you go. So this demonstrates an increasing amplitude makes the sound louder, and this demonstrates beautifully as well the compression of the air particles, the compression and the rarefaction, and you can see the sound wave progressing then longitudinally through the medium. Okay, so I'm going to control the displacement. I'm going to leave it where it is, and the next thing that so we've demonstrated loudness at this point. Then now we're going to demonstrate frequency. So I'm just going to increase the string tension, and that's precisely what you get. You get a higher pitch sound because the frequency through the string tension has increased. And you notice that the oscillations become greater. The frequency gets higher, the number of cycles per second, as we've demonstrated earlier on. And finally, extremely high frequency. Okay, so next you've got reflection, refraction and diffraction, three different properties of sound waves and light waves indeed, but sound waves here. So the first one that we're looking at is the reflection of sound, which is of course called an echo, and there's a couple of cool pictures here then, especially this one here, the sound mirror. So it's almost like a converging mirror. It collects the sound and focuses it to a point. And if you watch NFL, American football at all, you see there are ushers at the side of the field, and they have dishes similar to this pointed at the action on the field, so that they can collect the sound from the field, so they can hear exactly what's going on in the thumps and bumps and all this kind of stuff. And then they're recorded through a microphone. So this is reflection of sound. In any case, the sound waves hit the wall of the surface, and they are reflected back. Next you've got refraction, and refraction is easier to demonstrate with light waves actually, but in any case for sound waves it too can be demonstrated and witnessed, as in this statement: why can sound be heard more clearly on a cold night over water, which is cool, relatively cool, than on a warm day over land. Okay, this is explained by the refraction of waves. Okay, so these two neat little diagrams demonstrate refraction of sound. In the first case, the refraction is upwards, as in on a warm sunny day, and then on a cold night you've got refraction downwards. So to explain these then, it's pretty straightforward. Sun shines on the ground, the land heats up, and you've got warm air above the land basically. Much higher above that then, relatively speaking, you have colder air. Okay, so what happens is that in the elastic property of the air then, that is to say the vibration of the air particles is greater where the air is warm. Okay, and in that case the sound waves will travel faster then. You see that with the greater distance between, okay, these are meant to be wave fronts, these lines here, and you see in the warmer air underneath the red arrow, the spacings are greater, which means that the wavefront is moving faster in the warmer part of the air, and similarly it is slowed down because the wavefronts are closer together in the colder air. So therefore you just get a bending of the direction and the refraction is upwards. The opposite is the case then over cooler water. We're talking about water, which is thermally much more conductive than air, 5 times in fact. And so what happens is that the air over the cool water is cooled quite significantly, which then means that the elastic property causes the wavefronts, or the waves, the sound waves, to bunch together because they slow down. You can see the spaces decreasing here and increasing in the warmer air up here, and that causes the refraction, or the bending of the sound wave downwards, which means that you can hear better in cooler conditions. We all know that we can hear a sound from around a corner, which means that a sound wave is actually able to gradually turn around a corner. And so this is a property called diffraction, which means that if you have parallel wavefronts incident on a corner or on an edge, then on the other side of that edge the sound waves are going to try and occupy the space behind it, and how they do that is by turning. And if the opening is of the order of the same wavelength as the sound, then the transmitted wavefronts will actually occupy, they'll actually develop a curvature such that they'll occupy the entire space on the other side of the opening. Okay, for 2-point sources of waves, I've got this simulation here that demonstrates it really well. Okay, I've got it on slow motion right now, and you can see that you've got a black wavefront, it's completely circular, and then if you look closely you can see a white wavefront just being created. So one would be a crest and the other would be a trough. That'd be the idea. And you see another crest then appearing here. Now what happens is that you have 2 sources, and the 2 sources are going to be coincident on one another. In other words, they're going to cross one another at particular points. Okay, now if you look, you can see closely here that the white ones constantly cross one another there, the black ones constantly cross one another there, and that leads to constructive interference, and that's demonstrated by the red line here. That's where 2 crests or 2 troughs are coincident on one another, and they add together constructively, so you end up getting constructive interference. Okay, as opposed to the blue line that you see right here, this is where a black wavefront crest, let's say, and a white trough are coincident on one another, and you see that pattern being repeated right throughout here. And what happens there is you get destructive interference, where you get subtractive interference, and the 2 waves cancel one another out. So the red is these are lines of constructive interference, white with white, black with black, or if you like, crest and trough, and you get constructive interference, as opposed to the blue, which is destructive interference. That's a crest coincident with a trough. Okay, and that's exactly what the notes say. 2 traveling waves which exist in the same medium will interfere with each other. If their amplitudes add, the interference is said to be constructive interference, and the destructive interference if they are out of phase. And that's what we demonstrated. That was destructive was the white or the grey and the black, and the constructive was either black or grey. Okay, so that's what we're talking about there. Patterns of destructive and constructive interference may lead to dead spots and live spots in acoustics. If you strike a tuning fork and rotate it next to your ear, you will note that the sound alternates between loud and soft as you rotate, and that's quite true.